And since the late 80s, he has been working on the development and application of formal description techniques for interactive systems. Philippe is also the chair of the IFIP Technical Committee 13, and you know that Interact is the flagship conference of this committee. Today, Philippe is going to present a framework for designing perfect interactive systems with and for imperfect people, which is actually a hot topic since the operator is frequently considered as the main source of vulnerability in command and control systems. Here with me, there is also Helen Petri. She's connected online. She will chair me with me remotely. And so I give the stage to Philippe. Philippe.
Thank you very much, Carmelo. Hello, everybody. I think there is a bit of technical things to do. That was pretty quick. You can see the efficiency of the team here in Bari. So thank you very much for the invitation. Thank you very much for still being here. I'm impressed. I guess everybody wants to know where Interact 2023 will be, sorry. And we will know that after the presentation. So you have to stay here until the end of the presentation, including remote people for that. Yeah, so Carmelo said everything about the title and what? Ah, the mic. Is it better? Is it better? Oh, I can go backwards. Is it okay if I speak 1, 2, 3, 1, 2, 3, 1, 2, 3? I carry on. Yeah, but for the remote people, it's the same microphone, no? Ah, no, it's not. Okay. 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 So it's explainable multimedia technology. Okay, is it better? Okay, thank you very much. So I start again. I said, yeah, Carmelo said more or less everything about what I will be talking about. It's a framework for designing perfect interactive systems, knowing that the users might not be always perfect, unfortunately. And I will spend more time on trying to improve the system side than the user side, because a lot of people in psychology do this. And that's a bit outside of my field. In this presentation, I mean, we have this kind of motive here at the bottom, which is try to live as long as possible, because this way the time you will be dead will be shorter. Okay, and of course, when you use systems that are a bit critical, it's quite likely that you might die if the system is not perfect, let's say this way. So we should try to improve the quality of our systems in order to live longer and be dead as short as possible. So just to give you a bit of background, you have here a list of projects. It's not that important to read, but this is the kind of domain we've been working on, kind of command and control systems with directly industries developing and designing these systems, or manufacturers in the case of the aircraft. And you see that it's mainly air traffic management. It's also space domain, like ground segments for satellites, and civil aviation with large aeroplanes. So the talk today will be focusing on examples from large aeroplanes. And the work has been done by Airbus, jointly with Airbus people. And I will focus on the aspect of, I would say, perfect system in the context of a command and control system with an application with Airbus system. So unfortunately, as we all know, systems are not completely functioning perfectly so far. And even if they are not that complex, so that might be something we should question. Why simple systems don't work like the one we see now? And where we can go to try to get better systems in the future that will not be crashing miserably each time we try to use them. So one way of doing this, and we had a lot of presentation around that, would have to have autonomous intelligent systems like this SketchUp distribution system. And I don't know if you can see, but they could work well, but they usually it's not perfect either. So maybe going this way of artificial intelligence system doing everything instead of us might not be the right solution to the problem we are facing every day. I will take a very small example just for the introduction. This was my scene. I don't know if everybody has heard about that, but it was a time when I started my PhD. It was after the time, it was before the time I started my PhD, but it was still taught and explained. And it was a very nice system with artificial intelligence that was able, you can read, to detect some diseases and caused by bacteria. And what was interesting with that is that my scene technology has never been used in practice, but everybody has been taught this kind of technology at that time. And if you look for documentation, you can find documentation that tells you that the authors and people working in this domain at that time was saying that within 2 years, very few years, the doctors will be completely useless. Okay, and we don't need any doctor anymore. So we could have followed this recommendation and stop training doctors, and everything would be fine, more or less. Okay. So when we hear recommendation about something is really in 2 years, be careful. At least I'm extremely careful, because it reminds me always these kind of things that AI will solve everything in 2 years, and it's still there. So if we look at what Elon Musk has been saying about the autonomous cars based on AI technologies, in 2016 he was saying by 2017 every Tesla car will be fully autonomous, which was a good prediction, and the Germans got enough of this. And the German court ruled that Tesla cannot do any more advertising on full autonomous system because they don't deliver, okay? Which is good. So at least 4 years later, they decided to say that what was said to be done 2 years earlier would not be done, and so they should stop doing this, which is good. But if you have to go to the law and the courts to stop people talking rubbish, then it's a bit frustrating, I would say, to the least. So then the question is, if we don't go this way for having fully autonomous system, fully intelligent system in the next 2 years, what should we do? Us, poor humans, I mean, not the AI people, and us. So we could do different things. There are two things. One is a bit lazy, would be to wait. So you just wait for 2 years and everything is solved. Okay, so we don't have to write papers because there will be autonomous system writing papers instead of us. We don't have to present because the AI systems will build the presentation for people, or maybe at least for another AI system that will be listening to the presentation prepared by AI systems, so that you don't have to do anything and everything is solved. So that's one option, but you have 2 years, okay, to wait, because in 2 years it will be done. So if you don't want to wait for 2 years, we could do meanwhile some things during the next 2 years. So for instance, we stop listening to AI people and we do some things that could be useful, like for instance, helping users. That could be an option for all of us. And then we have to build interactive systems, tools, technologies that will help the poor users until the advent of AI that will solve everything in 2 years. Okay, but we still have 2 years of work, which is good, because I will be retiring not far away after that, so I can stop if AI systems are coming. So if we want to do some work during these next 2 years, I would propose a kind of small research agenda that we've been trying to investigate over the years. We have not been able to solve them, so we are much less good as AI people, because in 2 years they solve everything, but we have not been able to do that in 20 years, but we still carry on and dig into this. And I would argue that if we want to go closer, as close as possible to perfect systems, we need systematic approaches. Because we cannot say, oh, let's have an idea here, let's have another idea and try to bring the things together. And then when you have done half of the system, let's do another idea here and we put it inside, and that will not work. I mean, so we need systematic approaches for doing these things. We need also systemic approaches, because we cannot, I would argue, and I will present you why, we cannot slice problems. We can say, well, I will solve this small problem and then I will solve another small problem. And then when I put the pieces together, it will work. This is a Cartesian approach. I would argue it doesn't work. So we need to encompass everything in order to be sure that the solution we propose is correct. And if we look a bit more into the systematic approaches, in fact, we will need systematic approaches for design or identifying user needs, because we will help users. And this is the philosophy of the argumentation. So we need systematic approaches for design, for engineering, for evaluation, for deployment, for training people, and also for maintenance. Because we cannot say, I deliver a system and then I disappear, I do something else. No, the poor users will be still in front of the system and they will need updates, they will need corrective maintenance, etc., etc. So that would be the argument globally. And so in order to show you some concrete examples of things that we could do all together, I will present some principles on how to build perfect systems, kind of perfect systems, and then a very concrete example from aviation in the work that we have done. We have done on the cockpits. So the main principle, the first principle was in the title. It's the Poise Principle, and in the Poise Principle there are two things. So I put the definition in English, because I don't know if everybody knows the word. So the word is really that you should be calm and should have confidence. And if you are calm and you have confidence, then the thing will be okay. And this is poise. And you have two examples of the use of poise in sentences. So what do we have in the poise framework? Is that we have four main elements that have to be integrated and addressed all together. And I would argue again that we cannot slice the problem, and we have to put everything together. And this is the people. We have to look at the people. We have to look at the organization in which the people are working. We need to look at the interactive system people are using for doing the work they have to do for the organization. And we need to look at the environment where these people are working and where the interactive system are deployed. And if we don't take all of this together, then we will be in trouble by providing local solutions or local optimum to a big problem and then missing most of it. So the first important element, we don't need to hurry. So it's good because I said we have 2 years. In fact, now I can tell you if you follow Poise, we should take time. Okay, it will take time, but we will progress. And in the end, we will have something. And I would also argue that if we hurry, we will be in trouble. It might be dangerous either for the users or some side persons around the users. Like, for instance, I'm not saying anything, but autonomous cars could kill people. We don't know yet, but it's possible. So we should be careful, and not being careful and being in a hurry might be dangerous. I would give you just an example. An example of system that you might have heard or you might know is called Autoland. So most of the large aircraft nowadays implement a system which is called Autoland, which means that you can land automatically without any pilot intervention after setting up the landing. Okay, and you can see here some examples of things that were done with this system. So the early designs were in 1940. And it was certified as a type of system and a technology for system, having these 3 notions. I will come back on them, which is diversity, redundancy, and segregation. I will come back on them in 1968. Okay. So which is 30 years later. Okay. So that's interesting. And what you can see also that the certification was done on the 28th of December, okay, which is interesting. I mean, the people working in certification, they work. Okay. It's not people in a hurry. They do the work and they work until the system is reliable and dependable. There are some examples of this kind of thing. What is very interesting also for this Autoland, you see the limitations here for a 747 at the bottom. Okay, and the limitation tells you, in fact, if there is a bit of wind, Autoland doesn't work. But still, every aircraft is using Autoland and has Autoland embedded. So I will just show you a small video that you can find on YouTube. This is what can be seen from the cockpit. Okay, you see everything. It's working. Doesn't look like it, but it's working. So you see what the Autoland system is doing, okay, and hopefully, and we see also that we cannot see anything, okay, but the Autoland is functioning. It's not functioning. I told you interactive system don't work, and we have to work harder. That's a strange. It's moving the image now. Oh. Okay, I have a trouble. Anyway, I would skip. No, I'll come back. Try again. Thanks for trying to. Okay, so now you see better. So you will see this is the beginning. The system is doing things. You see that now we are getting closer. You see the landing gear is going down. So this is exactly what you will listen to when you will be seated in the aircraft when you come back. And this is what people can see from the cockpit. You see. Now the flaps are good. You see we are getting closer. Okay. We see better. Last checks, ready to land. You see, perfect view. Okay. Yeah, it looks good. So far, so good. Okay. So far, so good. You see. I think it doesn't work. 40 feet above ground. Okay, so we are very close. It's 200 feet, which is getting interesting. And you see, when you get to 200 feet, you start to see the landing. 200 feet is not a lot, so you are really close to crash, and the system is landing automatically. Okay, so that's an interesting aspect of an autonomous system. And what you see, of course, is that it's very useful. Is there is fog, and what is good is that there is never fog when there is wind. So you don't care if the Autoland system is not good when there is wind, because if there is wind, there is no fog, and you can land. But if there is fog, you need the Autoland system. So that's an interesting thing. Of course, I'm pretty sure if this was done not in 1968, but it was done in 2018, AI people would say, this is fully AI system, it's fully autonomous, and we can land every aircraft, etc., etc. It's not the case. There is no AI there. But people would say so, I'm sure, pretty sure. And this was Vienna Airport, just by chance. So if we look back to the Poise problem, or the Poise decomposition of problems, let's say this way, I could refine this, because if I stop with people, organization, and so on, it doesn't help much. So what we have been doing is to try to decompose this problem and to go into detail and also to look at the relationships between these different elements of the Poise system. And what we have here, so I will go quickly over it. So you have on top the organization, and of course you have organization types, and then you have a specific company, and the specific company will implement some specific work processes, workflows, etc., etc. So I will come back on that also later. If you look at the left or right-hand side, the IS side, you will see here again that we have types of systems. Of course, we are only interested in interactive systems. And then you have the type of command and control system, which are a bit specific. And then we will have a specific system that could be the cockpit of an aircraft, for instance, I was saying before. And this is the blue part that we have at the bottom of the IS. And then we have also the people. And the people is humans, usually. Sometimes we wonder whether the systems are done for humans, but this is for humans. We are considering only them. And then we have operators that have been following, for instance, as we can see, a specific training from the organization. And these people will have tasks to do. And if we consider this, we will see the interrelationships. As I said, people will be trained, and this is the responsibility of the airline, for instance, to train the pilots. Yeah, you cannot get a pilot in an aircraft and say, oh, try to do your best. Okay. So they will train people. People will be performing some tasks, following procedures, and there might be some automation, like the auto land. You can land manually, or you can land with the auto land system, or mixing the systems if you want. And you can see how all these elements fit together. And we can call it an interactive socio-technical system. And this is what was discussed already before in the conference. So now, if we consider imperfect users, we could also consider imperfect systems, like the one we have seen crashing miserably so far. And we could wonder what can go wrong. The answer is very easy. Basically, everything can go wrong. If you think about something, it will go wrong. That's the basic. So we have to be careful and to find systematic ways of addressing what can go wrong for each of these elements, okay, plus their interrelations. Okay, that's it. And the problem is that the devil hides in the details. So I cannot give you a generic solution. Okay, it will be always for a given system, for a given users doing a specific task for a given organization, which is in a certain state. That we will have some problem that we have to solve, okay, which is very good for us because there will be plenty of work to be done. So, and as soon as you move to another domain, there will be different problems that we have to solve. And again, we need to be systematic. So what I will try to do very quickly now is to go for these 4 elements, okay, and to try to identify how we can understand in detail this element, like interactive system, for instance, and then identify what can go wrong. And for everything that can go wrong, we try to find a solution, which is very close to what we do in HCI usually, which is to identify solutions to users having some activities to perform on the system, either for fun or for work, but that's a task we do. And we will do exactly the same here for all these elements. So I will start by interactive systems. So this is an interactive system that we have all seen, for instance. And if we want to have a schematic view, in fact, there will be a human in front of the system, interacting with the system and getting in the loop of this interaction. So this is the standard, I would say, software architecture for interactive system that you can find in the literature. It's called the ZI model or the Arch model, where we have the function that the system implements. Okay, and then we have an adapter to this set of function or database or whatever, and then we have the dialogue, which means what is feasible and what is not feasible, and what the user can do and how to change state, etc. And then we have what is presented to the users, so where we can have the input and output. So there were some discussions like, oh, if we have this kind of problem, we should look at people in software engineering. Don't do that. This is useless. They don't care. Okay, they're absolutely not interested in interactive systems. You can look at all the proceedings of ICSI, the International Conference of Software Engineering. Interactive systems are not of interest for them. So we have to work on that in order to find our solutions. So if we look at the HCI view, we will see that presentation, in fact, will be getting input from users and producing output towards users. Okay? And then we will have the core of HCI conferences, some of them, is interaction techniques. I have a great idea. I will have a new interaction technique. I make a user test, and then I have a new interaction technique that is interesting. So we can do a lot of work on that in order to try to improve performance of users, efficiency, etc. And if we look at multimodal interactions, we will have multiple input devices and multiple output devices. And we see that the architecture is getting a bit more complex. Okay. What we can see also, which is critical and extremely important here, is the notion of hardware. This is something that, for instance, was missing in some of the talks we had so far, where you see that the only problem that we have to solve is software. This is completely wrong. In interactive systems, the hardware part is critical. Each time you touch a mouse, a keyboard, or any kind of interactive system, we need to deal with hardware. And this is also why software engineering people will not help us, because they focus on software only. Okay? And hardware-software integration is a critical issue in interactive systems. Okay? Usually when we do design or we implement system, we don't care much because we work on standard platform, but this is not always the case. And people proposing new input devices, for instance, are explicitly dealing with this aspect of hardware-software integration and how to use that in a system. So if we look at the software architecture, it's getting a bit more complicated. And in fact, if we look at this diagram, things are missing. So depending on the type of the community I present this kind of work, I get different feedback. So what is missing? Users. Well, yeah, well done. If you go to, thank you. So if you go to dependable computing or software engineering conferences, they absolutely never find the user. This is something that they cannot get, but Carmelo was fully awake and aware, and we miss the user. And if we look at the users, now it's a huge part of the system with all the capabilities of user, cognitive, perceptive, motoric, etc., etc. And we have to deal with that and to address that. But there are still things missing, more difficult. What is missing is, again, hardware. So when you have a command and control system, we pilot things that are physical. Okay? We interact with things that are physical. So for instance, in an aircraft, you interact with the engines, and the engines are physical. And even if we have a mouse for interacting in this kind of aircraft, like this is a 380, and you see the trackball, which is called a KCCU, for interacting with the equipment in the cockpit. So if we look at this, what I have added at the right-hand side of the figure is what we call cyber physical systems. So this would be the engine. And if you start the engine, you're sitting in your cockpit, you feel the vibration of the engine. So you have a direct input on the user from this kind of system. And this is the case. This is the case in most of the systems you have. So that would be the case if you have a healthcare system, but it's also the case when you print. I'm sure everybody has done that. You print something, you don't hear the printer say something is wrong, okay? Because you have a user interface based on the hardware system you're monitoring. So this is the kind of global view that we have to address with two hardware parts that, again, unfortunately, people overlook completely, then completely overlooking the good solutions. Now we have seen the entire interactive system. If we think back about what can go wrong, we have to now have a way of identifying what goes wrong. So what goes wrong, we need to go to another community now. It's the community of dependable computing. And dependable computing people have identified descriptions of ways that go wrong. So I will go a bit faster, but this is called faults, errors, and failures. And if we follow this classification, a fault is something that happens. For instance, you have a cut of electricity. And then your system is in an error mode, for instance, the air conditioning system. But if this happens when there is nobody will notice. Okay? So we don't care. But if somebody wants to use the air conditioning, then you have a failure. The service is not delivered. And not delivering this service might cause other problems, like an explosion of a computer that was overheating, etc., etc. So that's why we have in command and control systems this notion of Christmas tree alarms. You get an alarm, and then you get plenty of alarms, and you don't know what to do because all the cascading of faults, errors, and failures. So this classification here is extremely interesting. And it relates a bit to the presentation from Ben when he was trying to identify threats, if you remember during the keynote. And we have here, but again, here you see what is very important. You can find on the dimension, hardware and software. So of course, we cannot overlook hardware. And so we have here classifications of groups of faults, and you have the left-hand side, which is during development, design and implementation, and during operation, when the system is delivered and people are using them for doing their work. And you can have faults of different types. And these different types of faults call for different disciplines, different types of knowledge that, again, if we do interactive system, we must integrate, otherwise we overlook part of it. So for instance, here you have the malicious attacks that can be done at development time. You have an Easter egg inside your program that will trigger some failure at some point in the future. Okay, a developer can do that. This is malicious. And that was also the presentation from Luca. The keynote was really addressing malicious behavior from people trying to degrade the performance of the system. And if you look on the other side, during operation, people can also do malicious things. So you might want to prevent people from doing rubbish, like inserting a USB key in a command and control system, ending up by having Brussels airport closed. Okay, you want to try to avoid this kind of thing. There will be methods for detecting and correcting development faults, and that would be relating to reliability. Fault tolerance is something different. There will be faults, and whatever happens, you cannot prevent them. So you have to deal with them and find solutions to detect, and if possible, remove them before the failure occurs. And here is where we play the bigger role, which is during operation, we design system that people will be used, and we try to avoid operator as error during the use of the system. The arrow I have been adding here is the kind of work that people in HCI, few people in HCI have been doing, which is to design systems for helping developers to don't do errors. Okay, so the arrows go from usability to development, and this is exactly the kind of work done by Brad Myers, and he has papers at the International Conference of Software Engineering to try to help developers by not adding faults, non-malicious, non-deliberate. So they don't want to do it, but they do it anyway. By having better interactive system like assistant for detecting APIs, for supporting the inclusion of systems. And if we want to deal with safety, we need to deal with all these kind of things together. And this was only, so I have examples, but I will skip them a bit quickly, but you can see why I'm talking. What is interesting is that I'm only dealing now with system side. And if I go to people, now I can see what HCI people, not all of them, but that would be the global work of your community, which is to think that people behave normally and they are reasonable and they don't make mistakes much. And we don't care that much about mistakes, which is in fact not always the case. And they will do mistakes for many different reasons. One could be what we have here. I hope most people know is the Maslow pyramid, where in fact, inside the people, they want to do things. Okay. And if you have to go to the restroom, you go to the restroom, whatever happens, you will do it. Okay. And it can go at different level, and people will behave how what they think is important for them. Also, there will be the 7 deadly sins. Okay, you can have a very nice system with nice people, but then you will understand that within the system, one person wants to be higher in the hierarchy, and they will try to squeeze all the other ones. And if you don't take this into account, then you will be in trouble again. And then if we classify them, we will have all the human errors classification plus the cognitive biases. And I will not go into detail again, but what is very important here is the notion of intention. So do you do it deliberately or not? And slip, lapse, and mistakes is not intentional. But it is for actions that you can do. So for instance, in designing interactive system, we might gray out a button, and this way the people cannot do the slips or the slip, for instance, or the lapse. Okay, so we will make actions unauthorized, so they don't do that. And this is an undesired outcome. So if we classify this by intention, authorization, and outcome, we can classify different types of errors, and we will see that we have these lapse and slips. I'm just skipping them a bit. The mistakes, the violations. So this is the landing on Hudson River, for instance. The pilot didn't check that both engines were down. He didn't do the procedure he was supposed to do, and thanks to that, it's likely that he was efficient enough to be able to land. Okay, so it was a deliberate violation of what he was supposed to do, and he didn't do it, and he saved the life of people. And then there is the cognitive biases that is intentional, authorized action, desired outcome from one person, but not for the other one. And usually it's unconscious. So people don't know they do this kind of cognitive bias. And if we look at the classification, which is the Codex of Cognitive Bias, there are more than 230. And you get this list here. And if we design systems, we have to deal with them, at least the ones which are relevant. And I give you some example here, which is the backfire effect or the Dunning-Kruger effect and the Hawthorne effect, for instance, that some of you might know. But this is the way it is. So Dunning-Kruger effect is a good example. The less you know a domain, the more you believe you know the domain, okay? Which is a bit dangerous if people start to talk about things they don't know, for instance, or they don't understand. Because they will first be wrong, but truly believe that they are right. And then you try to convince them, and they will have a backfire effect. You tell them, you're wrong, it's not this way. Yes, yeah, no. And then with the backfire effect, more you argue, the more they believe they are right. Okay. So this is to be taken into account if you want to train people or argue to people, etc. And the problem that this is not covered by the taxonomy I presented before from dependable computing. So we had to add all these elements in order to be able to address systematically the failures that people can trigger. And we have failures like inside the people. Okay. And I will skip a bit because I think I'm getting close to the time, more or less. Yeah. So this is a new classification we've been working on. If you want the detail on the paper, but there is a specific paper at the SafeCom conference on that. And we see now that we have been able to address all these aspects I was presenting before in one single framework, similar to the one on dependable computing. And I can give you some example of things that were not covered. For instance, aging. Okay, you have one user getting older, and the older he gets or she gets, then the performance is going down. Okay, there is no way we can do about it. This is why it's called a natural fault. You cannot avoid it. It will happen, and you don't know when, but it will happen. We have also here the cognitive biases. They are inside the body of people. So we can do something. That's why I was highlighting the word unconscious, because if you want to remove this cognitive bias, you have to make people conscious about the fact that this bias exists. Okay, so and we have to work on that in order to reduce their effect and try to make them disappear. And there are other ones, like here you see a natural fault imposed by the environment, which was the E of the Poise framework before, like a vibration. Okay, and I will directly jump on this example, because in the cockpit you have vibrations. The environment has an impact. And if we look at Laprise classification, a vibration is not having adding faults in the system. The system is functioning perfectly. But if you look at the users, they will degrade if they want to interact with the touch screen, for instance. Okay, so the fault is the vibration is impacting the human inside. And we have to deal with that and find solution. And now we go directly to this solution. So here is the solution, the example, let's say this way. This is a good example, just 1 second. It was about organization. So I skipped the part of organization because it's a bit too long, but you have here. And I was trying to argue in the beginning that we have a systemic approach. And the systemic approach, I have a good example, I believe, which is this one. It's a cockpit, again. And you see in the cockpit, as I said, there is a KCCU, and there is one for the captain and one for the first officer. Okay, and this is the trackball. And each trackball has a cursor. And you see here the cursor of the captain, which is the yellow arrow in the middle. Okay, interacting with a drop-down menu, which is a standard in interactive cockpits. And what you see here is the cursor of the first officer, which means that both can have the cursor on the interface and click at the same time, which might be a bit troublesome. But the rule by Airbus is that as soon as the captain cursor is in the screen, the first officer cursor is blocked. Okay. And why? Because the captain is the boss. This is a rule in the organization. And you see a rule in the organization going into the low level of interaction technique, which is a multimodal interaction technique with 2 mice, which is thing we have seen in HTI for many years. But here the interaction technique is tuned to reflect the work of the organization. So if you work in interaction techniques and you say, I don't care about the organization, I'm not interested in that, you're wrong. Because the organization might have an impact. So the concrete example I was talking about before is the vibrations. And again, you can see here the space. So this is a fully tactile demonstrator by Thales at the Bourget air show in 2011. And what you can see here is that Airbus in 2019, December 2019, they were delivering the first A350 with tactile screen. That was the first time they delivered an aircraft. So you see the number of years, which is again, I think, arguing for Poise. Okay? Not AI 2 years. This is not a good idea. Okay, so no hurry. It is a good idea. But I'm not talking about AI anymore because we don't care. So I will skip a bit, but now I will go quickly on solutions to the different problems altogether. Okay? So for instance, you want to have a tactile screen in a cockpit, which is good because it's lightweight with respect to all the buttons, etc., etc. So it saves a lot of fuel, and also it's easier to modify because you just change some interface element and then you have a new interface. The problem is that usually tactile screens that are currently available have a dependability of 5, sorry. And 10 minus 5, you have it here, so which is a failure of 5 minutes per year, for instance. And we want to go to 10 minus 9. What can we do? We need to reduce this. So what you can do, for instance, is to look at the hardware. And the hardware you will duplicate. So you have a technology on top of the other one. So if one is failing, you have another one that will be 10 minus 5 also. And then you reach 10 minus 9 because you need to have a fault in both of them in order to not be able to interact with the system. So this is an example on how we have to understand hardware and how we have to find solutions for hardware based on dependable computing, which is diversity, different elements. They are not programmed the same way. They don't behave the same. They are redundant. Both of them are providing the service, and they are segregated. If one is not functioning, it's not spoiling the other one and making it not work. Okay, that's the 3 main elements for dependable computing. An example of this, 3 minutes, okay. So I skip the example. It's about an interaction technique, but we don't care. So this is an example of vibrations I was talking about before. And we hear. We hear and we see the poor user. No, we don't see, unfortunately. But anyway, you would have seen that the guy is absolutely unable to select anything on the screen, okay, with the vibration that we were trying to have. So then we have to define an interaction technique that would be resilient to vibrations. And this is the brace approach. So instead of trying to interact, you put your hand on the screen, the interaction technique detects the 5 fingers, you hold yourself on the screen, and then you double tap with 1 finger, for instance. And this will improve, and you see here the results. You see that under vibration, brace, which is a small on the right-hand side, has nearly the same performance as when there is vibration. But if there is vibration and you don't have brace, it doesn't work at all. So this is an example, again, of the thing that could be done. So I skipped these elements. Last one I wanted to highlight is the fact that was on the left-hand side of the hierarchy of faults. It's developer faults. So if we do this kind of interaction technique, we cannot use things that have been done by others, like the double click on Windows. So we need to develop the new interaction technique. And usually this will be difficult. And if we don't do it properly, you might have faults inside the interaction technique. Like if you add undo, for instance, in your system, you will have a lot of line of code dedicated to the undo, and it's likely that there will be programming faults inside. So what we have to do is then to use formal methods, for instance, for defining exactly what is brace, and to be sure that there is no fault in the programming of brace. And these are models that we have been working on and building for ensuring the correct behavior of brace, which means it behaves as expected. And if there is a fault when you program it, you have possibilities by formal analysis to detect the fault and correct them. Okay. But I will not show you more details on that. I will skip a bit this, and I can go to the conclusion. So I'm nearly on time. I promised to Carmelo that I will be on time. Okay, so now the takeaway message and warnings, because there are more warnings than takeaway message. I was trying to show you some very local solutions, but I think what was more important is the global view on addressing the problem. Okay? How to go from one system we have to build for people in a given organization with a given environment, and how to make this system as good as possible and at least not crashing miserably like most of the system we use every day. So I would argue that I think we could leave AI people working on AI, and we still have a lot of work to do as HCI community to bring solutions to this problem. The second part is that you see contribution focusing on one property like UX or usability or dependability in their community is the same. I think there is no hope now. We need to integrate all of this together if we want to make systems that work. And we need to, as HCI designers, for instance, we will need to have an idea on how to implement the system and how to remove the faults that developers will integrate in the system. Okay, so Wendy, for instance, was arguing to have artists and designers, and I would say later, but let's have software engineers, dependable computing people, group people that can build the system. And if it's not perfect, then we can try to find other solutions. But at least we should be able to argue that the system we have been building is reliable. So it means that we need multidisciplinary, and you have some disciplines that we need to integrate, and nobody can integrate them all. So we have to work together with other people to make sure that this is implementable. The bad news is that the other ones, so far, they don't care. Okay, so if we don't take the responsibility on that, we will end up our life with miserable systems that don't work. And the field of HCI should, I think, not engage with another cognitive bias. It's called the planning fallacy. And the planning fallacy is that you overestimate the benefits and you underestimate the cost and the time, okay? Which I think it reminds something that I was trying to talk about before. The solution to this would be a solution in the long term would be to be able to have this kind of symbol, which is to say this interactive system is safe, it is usable, it has a good UX, etc., and I can have a stamp on it that it is certified to be good or to be perfect. And also we could have the other symbol, which is to stamp this person has done this system, paf, it doesn't work. Okay, you should not deliver it to users. Is that not the required quality for that? There was also a question to Ben, which I found very nice, which is, do you have an idea of a super tool? I have an idea of a super tool, because if people carry on programming things rubbishly and delivering to people that kill the other ones, the only hope for us is to be lucky. Okay? Because if you are lucky, you can escape. Even the other ones are doing rubbish, but you're safe. So I would propose that AI work on tools that make us lucky. Okay? That would be a very super. And closing, I have a data set, because they need data set for machine learning. And I have the data set, and I will just show you very quickly the data set. It's 30 seconds. I will only show you the first 3 elements of the data set that you have here. So nobody's killed in this video. So you see the guys, this is a good, AI should reproduce that, okay? This is important. So if the car is coming, you can escape. This is also very useful if you're not paying attention. AI should avoid you from being destroyed. This guy, lucky, this is lucky. This is also, if systems are not functioning properly and they are about to kill you, AI should avoid the accident, like you have seen here. In the case that people are not using the system correctly, AI should allow you to avoid. And this is the last one. And you see, if you are with a very good AI system, everything can be destroyed except the user. Okay. So we have the entire data set now. I think that we work on it, and in 2 years, it will be solved. This is good, so that's okay. So I would like to say special thanks to the colleagues that we have here. So people from the group, and some of them are here, like Celia, for instance. The people from Airbus, they have been working with us for more than 15 years now, so it's very nice. And also all the things on touch and so on was done by Carl and Andy. And the PhD student, Elodie, is here also with us. This is a picture of, if you work with industry people, you can have nice pictures that you can put on slides at the end. And I would like to thank you very much for the invitation.